What if one of the brightest clouds in the night sky wasn't a cloud at all, but an island universe larger than our own? How did astronomers mistake a galaxy for a smudge? What finally proved it was another Milky Way? And how did that one discovery reshape the size of the universe? For centuries, stargazers noted a faint glow in the constellation Andromeda. It didn't move like a comet, but it wasn't sharp like a star either. In 964 CE, Persian astronomer Al-Sufi documented it in the Book of Fixed Stars as a hazy little cloud. Nearly 1,000 years later, Charles Messier catalogued it as M31. Not out of wonder, but so other astronomers wouldn't mistake it for a comet. Back then, most believed it was just a nebula, a small local gas cloud within the Milky Way. But in the early 20th century, everything changed. Astronomers were divided over a fundamental question: how big is the universe? The debate reached its peak in 1920 with Harlow Shapley on one side and Heber Curtis on the other. Shapley insisted that the Milky Way was the entire cosmos. Curtis proposed that spiral nebulae like M31 were entire galaxies, far outside our own. Both had arguments. Neither had proof. Then came Edwin Hubble. Using the 100-inch Hooker telescope at Mount Wilson Observatory, the largest of its kind, Hubble found a game-changer: Cepheid variable stars inside Andromeda. These special stars act like cosmic beacons. By timing their pulses, Hubble could estimate their distance. And the result? Andromeda wasn't a part of the Milky Way. It was 2.5 million light-years away, a separate, vast galaxy filled with its own stars, planets, and mysteries. In a moment, that little cloud was transformed into a colossal galactic neighbor. Hubble's discovery didn't just settle a debate, it redefined our place in the universe. The cosmos wasn't just bigger, it was vast beyond comprehension, filled with billions of galaxies like our own, scattered across the darkness. That tiny smudge in the sky, it cracked open the universe. If you could step outside the Milky Way and look back, Andromeda is what you'd see. But is it just a mirror or something more? How does Andromeda compare to our galaxy? What makes it unique among the billions of galaxies out there? And why is it visible to the naked eye despite being millions of light years away? Say hello to Messier 31, better known as Andromeda, the closest spiral galaxy to us, and the largest within our local group of galaxies. It lies approximately 2.48 million light-years away. Yet it's so massive and luminous that you can see it from Earth with the unaided eye, appearing as a faint oval haze under dark skies. Astronomically speaking, that visibility is extraordinary. Light from Andromeda takes over 2 million years to reach us, meaning we're seeing it as it looked before humans even existed. Andromeda is classified as a barred spiral galaxy, like the Milky Way. It features a bright central bulge filled with older stars, surrounded by graceful spiral arms etched with interstellar dust, glowing gas, and ongoing star formation. A subtle bar of stars stretches through its center, helping funnel material inward. Nestled deep in the core is a supermassive black hole, estimated to be between 110 and 230 million times the mass of our Sun. Far more massive than the one at the heart of our own galaxy. But Andromeda isn't just large, it's gigantic. Depending on where you draw its outer boundaries, especially considering its dark matter halo, the galaxy spans between 150,000 and 220,000 light-years in diameter. That makes it noticeably broader than the Milky Way, which spans around 100,000 to 130,000 light-years. Andromeda is also far more populous. With an estimated trillion stars, it more than doubles or triples the Milky Way's count of 100 to 400 billion. These stars range from ancient red giants to bright blue newborns, scattered across its disk, halo, and satellite systems. Despite its grandeur, Andromeda isn't entirely serene. Its outer disk is warped. Its halo is peppered with stellar streams, leftovers from smaller galaxies it has torn apart. These features tell us that Andromeda is a galactic cannibal, having grown not just by forming stars, but by swallowing neighbours. And even now, it's moving toward us at over 110 kilometers per second. Not just a passing neighbour, Andromeda is on a direct collision course with the Milky Way, set to begin merging in about 4 to 5 billion years. So what is Andromeda? It's a mirror of ourselves, a window into our future, and a reminder that the universe is not still. It evolves, collides, and transforms. Why does Andromeda's heart seem to glow twice? And what invisible force sits between those lights? What creates Andromeda's double-core illusion? Is it hiding more than one black hole? And how does this oddity help us understand galaxy evolution? To the naked eye, or even a basic telescope, Andromeda's center appears as a typical bright galactic core. But high-resolution images from the Hubble Space Telescope revealed something unexpected. The core wasn't singular. It had two bright points, side by side like twin beacons. At first, astronomers were puzzled. Was it a binary black hole system? A recent merger? The reality was even more fascinating. Andromeda's nucleus contains a supermassive black hole, estimated to be between 110 and 230 million times the mass of the Sun. Surrounding it is a tight cluster of stars, many of which move in eccentric elliptical orbits, elongated loops instead of circles. These stars don't just scatter randomly. Instead, they bunch up near the same part of their orbit, specifically at periapsis, the point where they're closest to the black hole. Because so many gather there, it creates an illusion, a second, offset brightness. This isn't a double core in the traditional sense. It's a stellar mirage produced by gravitational choreography. Astronomers refer to this rare setup as a nuclear eccentric disk. Few galaxies show this phenomenon so clearly, and Andromeda offers a rare window into the mechanics of galactic centers. Beyond the core, we find a stellar bar stretching a few thousand light years. This isn't just decorative, it's a dynamic engine. The bar funnels gas and dust inward, potentially feeding the black hole or sparking new bursts of star formation in the dense inner regions. This central zone is also teeming with older, redder stars, many billions of years old, mixed with newer, bluer populations in nearby clusters. It's a hotbed of stellar archaeology, tracing the galaxy's long and messy past. Understanding the anatomy of Andromeda's core helps scientists model how galaxies grow, stabilize, and change over time, especially those like our Milky Way, which may share similar inner mechanics. So next time you glimpse that faint glow in the sky, remember, its heart isn't just bright, it's bizarre, brilliant, and full of motion. What if Andromeda isn't just a spiral galaxy? It's secretly wearing a ring. How can a galaxy's true structure stay hidden in plain sight? What secrets are exposed only in infrared? And what caused Andromeda's elegant arms to ripple into rings? At a glance, Andromeda is a textbook spiral, glowing arms coiling gracefully around a central bulge, streaked with dark dust lanes. Through amateur telescopes, you might catch a glimpse of this grand structure, delicate swirls frozen in time. But in wavelengths beyond visible light, a different picture emerges. Infrared telescopes, like Spitzer and others, reveal that Andromeda's arms aren't just spirals, they also appear as overlapping rings. These structures, invisible to the naked eye, form massive, looping arcs of stars, dust and gas. Some nearly complete, others broken like ripples on a pond. The most striking is the 10 kiloparsec ring, a circular ridge of star-forming material located about 30,000 light-years from the center. This ring doesn't pop in optical wavelengths, but in infrared and radio it glows vividly. So how did it form? One explanation is that a smaller satellite galaxy, possibly M32, once plunged through Andromeda's disk, triggering shockwaves. Like a pebble dropped into a still lake, this event would have sent ripples outward, compressing gas into ring-like waves. These rings may persist for billions of years long after the intruder passed through. Another theory involves density waves, slow-moving patterns of compression that roll through a galaxy's disk, shaping stars into elegant spirals and rings. These gravitational waves sweep up gas, creating pressure zones where stars ignite. The result? Enormous stellar nurseries. These regions are packed with H2 clouds, vast glowing areas of ionized hydrogen where young hot stars are being born. Within them, blue giants flare into life, illuminating nearby dust and eventually dying in brilliant supernova. This hidden ring system isn't just a pretty feature. It's a record of Andromeda's past interactions and a map of where it's still actively evolving. It shows that galaxies aren't static. They're living systems, sculpted by gravity, collisions, and waves of starbirth. So while the spiral arms get the spotlight, it's the hidden rings, the ones you can't see without specialized eyes, that reveal Andromeda's deeper secrets. Is Andromeda really the heavyweight of the local group? Or has the Milky Way been quietly bulking up? How big is Andromeda, really? How do astronomers measure its size and mass across millions of light years? And could the Milky Way actually be more massive? For decades, Andromeda was the clear heavyweight of our galactic neighborhood, the local group, a dominant spiral galaxy towering over our own Milky Way. But the more astronomers measure, the more the story changes. Let's begin with scale. Andromeda's visible disk spans between 150,000 and 220,000 light-years across, depending on where you mark its faint outer edge. Include its dark matter halo, and the diameter may extend beyond 600,000 light-years. That's enough space to fit the Milky Way inside and still leave room for hundreds of thousands of light-years of darkness. Its stellar population further suggests dominance. Andromeda contains roughly 1 trillion stars, vastly outnumbering the Milky Way's 100 to 400 billion. This sheer number is one reason it appears so luminous in long-exposure images. Every speck of starlight counts. But star count isn't the same as mass. Andromeda has a huge dark matter halo, just like the Milky Way. For years, the consensus was that Andromeda had around 2 trillion solar masses, while our galaxy had about 1 trillion. That imbalance made it the gravitational anchor of the local group. But recent research, leveraging data from missions like Gaia and advanced models of satellite galaxy motion, suggests the Milky Way may be much heavier than previously believed. Some models place both galaxies in a similar range of 1.2 to 2 trillion solar masses. Some even put the Milky Way slightly ahead. Why the shift? Measuring a galaxy's mass is incredibly difficult. Much of the mass is invisible, made of dark matter that doesn't emit or absorb light. Astronomers infer its presence by observing the motions of stars, globular clusters, and orbiting satellites. And small errors can cause big swings in final mass estimates. Andromeda's mass isn't concentrated in just one place. It's spread across a bulging central core, a flattened stellar disk, an extended stellar halo filled with globular clusters, and an even larger dark matter halo that exerts long-range gravity. That outer halo tells a violent story, riddled with stellar streams, long ribbons of stars left behind by cannibalized dwarf galaxies. Andromeda has grown by feasting on its neighbors. As for its age, Andromeda likely began assembling more than 10 billion years ago, forming from merging protogalaxies during the universe's early turbulent phase. So how big is it? Big enough to dominate ancient sky myths, big enough to anchor a galactic family, and big enough to remind us that in space, even the titans are hard to weigh. What does a trillion stars look like? And why is Andromeda's cosmic factory slowing to a crawl? Why does a galaxy with more stars form fewer new ones? Has Andromeda already peaked in its life cycle? And what happens when a galaxy starts to run out of fuel? At a glance, Andromeda seems unstoppable, a luminous titan with nearly 1 trillion stars, larger and seemingly more massive than the Milky Way. But beneath its glow, a quiet truth reveals itself. Andromeda is slowing down. Its once roaring engine of star formation is now a gentle hum. Despite its size, Andromeda forms stars at a surprisingly modest rate, around 1 solar mass per year. The Milky Way, though smaller in stellar population, forms new stars at 3 to 5 times that rate. For a galaxy that's burned so brightly for billions of years, this marks a dramatic slowdown. So what's happening? The answer lies in fuel depletion. Stars are born from cold hydrogen gas, the essential ingredient for stellar nurseries. Over time, Andromeda has used up, heated, or blown out much of its supply. Some of that gas was consumed in past starbursts, intense periods of formation triggered by galactic mergers or internal dynamics. Other portions were expelled by supernovae, which can launch gas far into the halo or even eject it into intergalactic space. What's left is more diffuse, warmer, and less capable of collapsing into new stars. The stars it does produce now are mostly low-mass red dwarfs. These tiny stars burn slowly and steadily, living for trillions of years, but they lack the youthful brilliance of hot blue giants. And as Andromeda's population of short-lived massive stars fades without replacements, its overall color shifts from white-blue to red-orange. Astronomers call this transformation galactic aging. Galaxies pass through a life cycle, youthful and blue when rich in gas, then maturing and reddening as star formation wanes. Eventually they enter a phase known as quiescence, where almost no new stars are born. Andromeda is likely in the middle of this transition. It's not red and dead yet, but it's no longer youthful. Still, a galaxy with 1 trillion stars is far from lifeless. Within that immense population are likely billions of planetary systems, some orbiting young stars, some clinging to ancient suns. If life has found a way elsewhere in the universe, Andromeda is a prime candidate to host it. Moreover, this slower pace may actually foster cosmic stability. In regions where stars form more slowly, radiation and stellar violence decline, allowing planets to orbit in peace for eons. So while Andromeda may be winding down, it's not fading away. It's evolving, maturing into a quieter, steadier phase, a galactic elder, still brilliant, still active, but no longer chasing the energy of youth. And in that quiet, it may carry the wisdom and the worlds of countless cosmic generations. If you want to know a galaxy's past, count its trophies. How many smaller galaxies has it devoured? Why does Andromeda have more globular clusters than the Milky Way? What are those strange tidal streams in its halo? And how does a galaxy eat its neighbors? Galaxies don't grow peacefully. They collide, consume, and reshape themselves by absorbing smaller systems. And few galaxies show this more dramatically than Andromeda, a cosmic cannibal whose satellites, globular clusters, and tidal streams map out a long and violent history. Let's start with the globular clusters. Dense, ancient spheres of stars that orbit the galactic core. The Milky Way hosts about 150 to 200 of them. Andromeda? It has over 450 confirmed clusters, possibly more. These clusters are among the oldest structures in the universe, with many formed over 12 billion years ago, before galaxies had even fully settled into shape. But Andromeda's abundance may not be natural. Many of its globulars likely came from other galaxies, captured during mergers and stripped from their original homes. That leads us to one of the most striking signs of galactic cannibalism: tidal streams. These are long ribbon-like trails of stars that arc through Andromeda's stellar halo, the vast region beyond its visible disk. Each stream is the remnant of a dwarf galaxy pulled apart by gravity. As the smaller galaxy spirals in, its stars are gradually stripped and smeared across space. Modern sky surveys, like PANDAS, Pan-Andromeda Archaeological Survey, have mapped dozens of these streams. Some stretch across tens of thousands of light years. To the eye, they're faint wisps. But to astronomers, they're forensic evidence of Andromeda's violent growth. Among Andromeda's most well-known satellite galaxies are M32 and M110, elliptical companions locked in a complex gravitational dance. M32, in particular, is unusually dense and compact. Some researchers believe it's the naked core of a once larger galaxy that Andromeda stripped clean. If true, M32 isn't just a satellite, it's a survivor. In addition, Andromeda is surrounded by at least 30 dwarf spheroidal galaxies, tiny, dim companions with low masses and little gas. Some are barely visible. Others are already unraveling, caught in the act of being digested by Andromeda's vast halo. Why does this matter? Because it reveals how galaxies like Andromeda and our own Milky Way grow. They don't build themselves from scratch. They assemble over billions of years through accretion, mergers, and cosmic scavenging. Andromeda simply shows its history more clearly. Its halo is messier, its streams more pronounced, and its satellite system more extensive. Every cluster, every arc, every shattered dwarf tells the same story. This galaxy is a survivor of many small battles. So yes, Andromeda is majestic. But behind its graceful spiral lies a brutal past, a past written not in myths, but in the motion of stars and in the quiet disappearance of smaller neighbors. If the Milky Way can host at least one living planet, how many more might be hiding inside a galaxy with 1 trillion stars? Could alien civilizations exist in Andromeda right now? How many potentially habitable worlds does it contain? And what would it take to detect life from across the void? We live in a galaxy that produced life, at least once. So when we look at Andromeda, with its staggering scale, rich stellar diversity, and billions of years of cosmic history, it raises a profound question. Is anyone over there? Let's begin with the math. Andromeda contains roughly 1 trillion stars, more than double the estimated population of the Milky Way. Observations from missions like Kepler and TESS suggest that most stars host at least one planet. That puts the likely count of exoplanets in Andromeda at well over 1 trillion. Now zoom in further. Consider the habitable zone, the narrow band around a star where temperatures are just right for liquid water. Even if just 1% of stars have an Earth-like planet in this zone, that's 10 billion potentially habitable worlds in one galaxy alone. And those are conservative odds. Some stars may host multiple habitable planets. Others may be surrounded by exomoons, large natural satellites that could also sustain life. And some of the most common stars in the universe, red dwarfs, burn slowly and steadily for trillions of years, offering long windows for life to emerge and evolve. Andromeda's stars are a mix of old and new. Its metal-rich regions have undergone billions of years of stellar recycling. Explosions that scatter heavy elements into space, fueling the next generation of planet building. This gives life the raw ingredients it needs: carbon, oxygen, nitrogen, and more. Statistically, it's hard to argue against the probability of life, perhaps even intelligent life, somewhere in Andromeda. But could we detect it? Unfortunately, not yet. Andromeda is 2.48 million light-years away, far beyond the reach of our current exoplanet hunting telescopes. Even with advanced spectrometry, we can't yet isolate individual planets in another galaxy, let alone analyze their atmospheres for biosignatures like oxygen or methane. Still, hope isn't lost. Future missions like LUVOIR, HABEX, or even interferometry-based telescopes could eventually peer deeper. One day, we might spot a faint, telltale sign in a spectrum, a wobble, a reflection, a hint of molecules that shouldn't be there unless life exists. Until then, all we can do is imagine. Maybe there are oceans on alien worlds reflecting the light of twin suns. Maybe ancient civilizations built their own observatories, wondering about us. Or maybe we're all alone, for now. But when we look at Andromeda, we don't just see stars, we see potential. 1 billion unanswered questions. A silent galaxy that might be teeming with stories, waiting to be found. What happens when two spiral giants collide, and will Earth survive to see it? Is Andromeda really on a collision course with us? What does a galactic merger look like? Will stars crash? Will black holes collide? And where does our solar system go when everything rearranges? Right now, the Andromeda galaxy is hurtling toward us at about 110 kilometers per second. Unlike the majority of galaxies in our expanding universe, Andromeda is blue shifted, a rare sign that it's coming closer, not moving away. This isn't just a near miss, it's a direct hit, set to unfold in slow motion over the next 4 to 5 billion years. The Milky Way and Andromeda will eventually merge, creating a brand new galaxy. It won't be violent in the way we imagine collisions on Earth. Space is mostly empty, and individual stars are unlikely to collide. But the gravitational ballet will be nothing short of spectacular. As the two galaxies begin to interact, their massive halos will touch first. Dark matter and gas will feel the tug. Then, like dancers spiraling closer, the disks will interpenetrate, triggering tidal forces that stretch stars into long arcs and streams. Multiple passes will follow. Each time the galaxies swing around one another, more structure will be stripped away. Spiral arms will distort, tails will stretch, and gas clouds will collide, compressing into intense star-forming regions. Cosmic fireworks igniting new generations of stars. Over roughly 6 billion years, this celestial duel will end in unification. The final product is expected to be a giant elliptical galaxy, round, featureless, and glowing with the light of merged histories. Astronomers have already named it Milkomeda, or sometimes Milkdromeda. It will be a colossal structure, potentially stretching over 500,000 light years across, filled with the remnants of both galactic civilizations. At the center, two monsters will meet. Sagittarius, a star, the supermassive black hole at the heart of the Milky Way, and Andromeda's even larger black hole, estimated to be between 100 and 230 million solar masses, will spiral inward, locked in a death waltz. Their eventual merger will release a torrent of gravitational waves, rippling through space-time like cosmic thunder. Observatories like LISA may one day detect such events across the universe. But where does that leave us? By the time Milkomeda forms, Earth may no longer exist. Our Sun is predicted to swell into a red giant in about 5 billion years, vaporizing the inner planets, including Earth. The planet you're standing on will be long gone before the final galactic reshaping begins. Still, the solar system itself may survive the galactic upheaval. If the Sun remains gravitationally intact, it may be flung into a wildly different orbit, perhaps into Milkomeda's outer halo, or even ejected entirely, becoming a rogue star wandering intergalactic space. Simulations suggest that between 10% and 30% of stars could be flung far from the galactic core. That includes ours. The night sky, if it still existed, would transform. Familiar constellations would vanish, replaced by a chaotic spread of unfamiliar stars, arcs, and glowing tails. And yet, from the surface of some distant planet orbiting a star that does survive, the view of this merger could be breathtaking. Sweeping tidal tails, glowing starburst regions, and two galactic cores entwining like pearls in space. It would be the greatest light show in the universe, and utterly silent. There are no sonic booms in space, no crashing sounds, just the invisible pull of gravity reshaping the cosmos over billions of years. For future civilizations, if they exist, the merger might represent opportunity. New stars, new systems, and perhaps even new habitable zones could arise from the chaos. What seems like destruction is, in truth, cosmic recycling. And there's beauty in that. Even though Earth will be gone, the atoms that once made up oceans, forests, and people will survive. They'll be part of dust clouds, part of new stars, new planets, new possibilities. Milkomeda will be our legacy, a monument to two galaxies that once danced through the cosmos, carrying life, curiosity, and the seeds of something more. Two spiral giants side by side in the local group. Same species, different personalities. How do Andromeda and the Milky Way truly compare? Which one is bigger, more massive, older, or more active? And why does one make more stars, while the other holds more stars? On paper, Andromeda, M31, and the Milky Way seem like twins. They're both barred spiral galaxies, each with hundreds of billions of stars, spiral arms, dark matter halos, and supermassive black holes at their centers. They orbit the same local group center of mass and are locked in a gravitational bond that will eventually lead to their merger. But the similarities end quickly. Andromeda is the more popular sibling, with an estimated 1 trillion stars compared to the Milky Way's 100 to 400 billion. Its greater stellar count gives it a brighter and more sprawling appearance in telescopic imagery. Strangely, despite having more stars, Andromeda forms fewer new ones. Its SFR hovers around 1 solar mass per year, while the Milky Way forms 3 to 5 solar masses worth annually. In this regard, the Milky Way is more cosmically active, still building stars at a healthy clip. Andromeda's central black hole is also more massive, over 100 million solar masses, compared to 4.3 million for the Milky Way's Sagittarius A star. This huge disparity may reflect different merger histories or core dynamics. Andromeda has a more disturbed halo filled with stellar streams and merger remnants. It's messier, more obviously shaped by past collisions. The Milky Way, while not untouched, appears more structurally coherent, perhaps because our vantage point is from inside it. Andromeda's disk is broader, reaching up to 220,000 light-years across, compared to the Milky Way's 100,000 to 130,000 light-years. Yet when dark matter is included, both galaxies fall in a similar total mass range, about 1 to 2 trillion solar masses. The Milky Way might contain slightly older components, like globular clusters and stellar halo stars, but both galaxies began forming more than 10 billion years ago, shaped by billions of years of mergers and evolution. They are different, but equal. Rival galaxies with contrasting traits, destined to become one. Want to see another galaxy tonight? No telescope required? Where is Andromeda in the night sky? When is the best time to spot it? What will you see with your eyes, binoculars, or a telescope? And what should you expect? If you've never seen another galaxy with your own eyes, Andromeda offers a rare invitation. It's the most distant object visible to the naked eye, a staggering 2.48 million light-years away, yet it still shows up as a faint glow in our skies. To find it, you'll need dark skies, ideally far from city lights, and a little patience. The best time is in the Northern Hemisphere's autumn months, especially from late August to early November, when Andromeda rises high in the evening sky. Start your search by locating Cassiopeia, the distinctive W or M shape formed by 5 bright stars. From the central peak of that W, trace a line downward toward the Andromeda constellation. About halfway between Cassiopeia and the star Mirach in Andromeda, you'll find a subtle oval smudge. That's Messier 31, the Andromeda galaxy. To the unaided eye, it resembles a faint cloud or a ghostly blur. But that light has traveled millions of years to reach you, and it comes from 1 trillion stars shining together. Binoculars enhance the experience dramatically. A pair of 7 by 50 or 10 by 50 binoculars will reveal its full, stretched out shape. Most people are surprised to learn that Andromeda actually spans a larger area of sky than the full moon, its faint edges just harder to detect. With a small telescope, you won't see individual stars, but you can observe the bright central core, some hints of the dust lanes, and 2 satellite galaxies, M32 and M110, orbiting close by like faint companions. If you're in the southern hemisphere, Andromeda becomes a tougher target. it never rises above the horizon below -40 degrees latitude. Between the equator and -40 degrees, try observing it in the northern sky during November, just after sunset. There's nothing quite like seeing another galaxy with your own eyes. It's humbling, it's surreal, and it's a reminder that the universe is not just something we study, but something we're part of. Why do deep images of Andromeda reveal faint glowing arcs, ghosts in our sky or echoes from M31? What are these strange filamentary arcs near Andromeda? Are they part of the galaxy or something closer? And what do they tell us about the space between stars and between galaxies? When astronomers aim narrowband filters at Andromeda, particularly those tuned to O3, doubly ionized oxygen, and H-alpha, ionized hydrogen, they often find something unexpected: faint arcs, filamentary wisps, and ethereal glows in the sky near the galaxy. At first glance, these features look like they belong to Andromeda. Their shape and location seem to suggest they're part of M31's extended halo. Maybe ancient outflows, feedback-driven winds, or stellar remnants from long-past mergers. Some even stretch well beyond the optical disk of the galaxy, curling like ghost trails across deep sky mosaics. But here's the twist: many of these arcs may not be part of Andromeda at all. They might actually be foreground features, floating within our own Milky Way. Known as galactic cirrus, these delicate clouds of diffuse ionized gas and interstellar dust hang between the stars, glowing faintly when illuminated by background starlight, or bathed in the galactic radiation field. These clouds are normally invisible, but deep, long-exposure astrophotography, especially using narrow-band filters, can bring them to life. And because they lie in the same direction as Andromeda, they can appear to overlap, creating an illusion of connection. Distinguishing between local and distant features is tricky. Astronomers rely on spectroscopy, using the Doppler shift of the gas's emission lines to measure radial velocity. If the arc's motion aligns with M31's recession speed, it might be extragalactic. If it matches the Milky Way's gas velocities, it's local. But in some cases, the results are ambiguous. The velocities overlap, the structures are too faint, and we're left with a genuine mystery: cosmic filaments with uncertain origins. Why do they matter? Because these features offer insight into how galaxies breathe, how they absorb, expel, and interact with the matter around them. They hint at intergalactic interactions, gas recycling, and the hidden complexity of what we often call empty space. So when you see a deep photograph of Andromeda, look closely. Behind the familiar disk may be a web of whispers, gas, dust, and ionized light, revealing a universe that's far from empty. At 2.48 million light-years away, Andromeda is our cosmic neighbor. But could we ever go there? How long would it take to reach Andromeda? Could future technology get us there faster? Or are there theoretical cheat codes that might make intergalactic travel possible? Reaching another galaxy might sound like science fiction, and for now it is. Even our fastest spacecraft, Voyager 1, is traveling at about 17 kilometers per second. At that speed, it would take over 44 billion years to get to Andromeda, more than 3 times the remaining lifespan of the universe. But let's stretch our imagination. What if we could build a probe that travels at 10% the speed of light? An idea explored in Breakthrough Starshot, a proposed mission using laser-driven light sails to propel tiny spacecraft. Even then, it would take about 25 million years to reach Andromeda, That's better, but still too long for any human crew or real-time science return. Could we do better? Advanced propulsion concepts like fusion drives, antimatter rockets, or Bassard ramjets theoretically promise higher fractions of light speed, but they all present enormous challenges: fuel storage, energy output, radiation shielding, and decades-long maintenance in deep space. Even if solved, time remains a barrier. So what about warp drives or wormholes? Theoretical physics entertains ideas like the Alcubierre drive, which would compress space in front of a ship and expand it behind, allowing faster than light travel without violating relativity. But such technologies demand exotic matter and negative energy densities that may not exist, or may be impossible to control safely. So if travel is out, is there another way? Yes, observation. With future telescopes like LUVOIR-HABEX or ultra-long baseline interferometers, we may one day resolve individual planets in Andromeda, analysing their atmospheres for biosignatures like oxygen, methane, or chlorophyll-like pigments. We may never walk on an Andromeda world, but we could see its sunsets, detect its climates, or even catch signs of alien civilizations using only light. Andromeda challenges us to think bigger. It's not just a destination of distance, but a destination of imagination. A frontier we'll cross not with rockets, but with curiosity, data, and dreams. What if understanding Andromeda is the key to unlocking the Milky Way's future? Why do astronomers study Andromeda so closely? What can a neighbouring galaxy reveal about the past, present, and fate of our own? And how is it more than just a pretty spiral in the sky? To the casual stargazer, Andromeda is just a faint smudge of light, a cosmic ornament on autumn nights. But to astronomers, it's a mirror, a model, and a warning. Andromeda is close enough to study in detail, yet far enough that we can view its entire structure in a single frame, something we can't do with our own galaxy. From its sprawling halo and spiral arms to its turbulent core, Andromeda offers a complete, high-resolution blueprint of a galaxy similar to ours. Andromeda helps us test galaxy formation theories. Its stellar streams, remnants of smaller galaxies it has consumed, are fossil records of galactic mergers. These structures confirm that large galaxies grow through accretion and collisions, the same process that built the Milky Way. Its vast dark matter halo lets us probe the invisible architecture that holds galaxies together. Its supermassive black hole, 20 to 50 times more massive than Sagittarius A star, provides a contrasting case study in how black holes grow and affect their environments. Andromeda's relatively low star formation rate, despite its massive size, teaches us about quenching, the process by which galaxies shut down stellar birth. Studying this transition helps us understand the life cycles of galaxies and whether the Milky Way may follow the same path. But perhaps most importantly, Andromeda shows us our future. In 4 to 5 billion years, the Milky Way and Andromeda will merge, reshaping both galaxies into one. Every feature we see in M31 today may echo what we'll experience tomorrow. Watching Andromeda is like reading a future diary of our own home. It also ignites something deeper, wonder. A faint smudge in the night sky contains 1 trillion stars, billions of planets, and possibly countless forms of life, all orbiting a galaxy on a direct path to join ours. It's a symbol of connection, curiosity, and cosmic evolution. Andromeda isn't just another galaxy, it's the closest version of us in the universe. 1,000 nights from now, you'll still see it, a soft smear in the sky, But someday, that distant galaxy will become part of our own. What does Andromeda mean in the grand story of our universe? Why does its presence stir something so human in us? And what does it truly mean to say, it's coming home? Every clear night, Andromeda rises, a subtle glow just above the tree line. It doesn't blink, twinkle, or shout. It waits, silent, ancient. That light left Andromeda more than 2.4 million years ago, back when early humans first began to walk upright on Earth. It's traveled across space and time through intergalactic emptiness to fall on your eyes tonight. And for centuries, we didn't know what we were looking at. The ancient Persians called it a little cloud. Early astronomers marked it as a smudge, a nebula, a maybe comet. Then came the revelations. It was a galaxy, a vast island of stars, a cosmic sibling, a future partner. Because Andromeda is not just drifting in space, it's moving toward us. In about 4 to 5 billion years, it will merge with the Milky Way. Stars will be flung into new orbits. Gas clouds will collide, triggering supernovae and bursts of new stars. Central black holes will dance, spiral, and eventually unite. And from the chaos, a new galaxy will be born, Milkomeda. By then, the Earth may no longer be habitable. The Sun will be nearing its end. But the atoms that make you, carbon, calcium, iron, will still exist, floating in space, drifting in stardust, recycled into new forms. Andromeda reminds us that the cosmos is not static. It evolves, collides, rebuilds. It teaches us that galaxies, like people, have life stories, that even in isolation, we're never truly alone, that everything eventually comes together. Tonight, you can look up and see it with your own eyes. No spacecraft required. That faint smudge? It's not just light. It's a reminder that you live in a galaxy that's alive, that you're part of a story that spans eons, and that across the cosmos, something vast is always reaching back. Subscribe, hit the bell, and let's keep chasing the stars together.